A warm welcome to the lecture on the subject of wavelets and multirate digital signal processing, in which we intend to build further the connection between signals or functions in L2R and vectors, and therefore, we wish to build further the idea of thinking of functions as belonging to linear spaces and characterizing them in a manner slightly different from what we were doing in the previous lecture. So, just to put our discussion in perspective, this is the fourth lecture on the subject of wavelets and multirate digital signal processing, and what we intend to discuss in this lecture is the following. Let me put down the points one by one. The first thing that I wish to talk about today is to think of functions as generalized vectors. This idea is going to be useful to us in many different contexts in this course. So, we need to understand this connection between functions or signals and vectors in depth. We shall spend some time on it today. Secondly, the connection between L2R functions, connection or connections between L2R functions and sequences. We wish to understand this in greater depth. So, what we are going to show in the latter part of this lecture is that one can intimately relate processing of a function to processing of an equivalent sequence, and whatever we are doing to try and gain information from or modify a function can be done by equivalently processing or modifying that sequence corresponding to the function. Let us then embark on the first of these two objectives now. You see, let us begin by asking what characterizes a vector after all. Let us take a minute and reflect. What characterizes a two-dimensional vector, for example? A two-dimensional vector is essentially characterized by two coordinates which are independent. We call them perpendicular coordinates. Actually, the idea of perpendicularity there is also intimately related to the idea of independence. So, for example, let me treat the plane of the paper as a two-dimensional space. So, the two-dimensional space corresponding to this paper. Well, let us take any vector on this two-dimensional space. So, let this vector be V, I am marking it as V. There are many different ways to characterize this vector. In fact, notionally an infinite number of ways, and one of those ways is to choose the following two so called perpendicular axes. So, we choose one axis like this and another axis like this, and choose a unit vector along each of them. So, I have say a unit vector, let me call it u1 cap along this axis, and another unit vector u2 cap along this axis, and then I could write v1 or I could write this just the vector v uniquely as say v 1 times u 1 cap plus v 2 times u 2 cap, whereby v 1 and v 2 characterize this vector v uniquely in this two dimensional space with respect to the coordinate system generated by u 1 and u 2. And there is an infinity of such coordinate systems. In fact, one infinity of such coordinate systems can be generated simply by rotating this coordinate system of u 1 u 2. It is very easy to see that if I take this structure u 1 u 2 and rotate it by any angle in this two dimensional plane, it would give me a new coordinate system. So, there is an infinity of orthogonal coordinate systems in two dimensional space, and in fact, there is also a relation between all these infinite orthogonal coordinate systems. Simple enough. And orthogonal coordinate systems are not the only kinds of coordinate systems for a two dimensional vector. So, for example, the same two dimensional space can be described by the following different coordinate systems. So, I will draw the same vector v. And it is perfectly all right to choose a coordinate system something like this. I could choose one coordinate like this and another coordinate like this. And of course, I could again have the unit vectors in these two directions, u 1 cap so to speak, u 2 cap, and I could express v in terms of u 1 cap and u 2 cap. Indeed, I could complete a parallelogram here. So, using the parallelogram law, I could draw a line parallel from the tip of this vector to this u 2, another one parallel to u 1 from the tip of the vector, and it is very easy to see that this dot dash vector here plus this dot dash vector here gives me v. So, let me highlight that dot dash vector. This vector here plus this vector here gives me v. Let me call this v 1 tilde, and it is a vector, and let me call this v 2 tilde, that is again a vector. Of course, we have v is v 1 tilde plus v 2 tilde, and it is very easy to see that v 1 tilde as a vector is some multiple of u 1, and similarly v 2 tilde as a vector is some multiple of u 2. Thereupon, I have v is some multiple of u 1 plus some other multiple of u 2. K 1 u 1 plus k 2 u 2. The only catch is determining k 1 and k 2 is a little more difficult than determining the constants in the previous representation. In fact, let me go back to that previous representation. I had this representation previously, where v is v 1 u 1 cap plus v 2 u 2 cap. And remember, v 1 and v 2 here of course, are constants and very easy to obtain, because I can simply obtain them by taking a dot product of v with u 1 cap and v with u 2 cap. So, in fact, in the sense of dot products, V 1 is indeed V dot u 1 cap, and V 2, I mean V 1 as a coordinate, not as a vector, V 2 as a coordinate is the dot product of V with u 2 cap, simple enough. Such a simple relationship does not exist in this context. While we are not hard put to describe the process by which we obtain K 1 and K 2, it simply says construct a parallelogram. Expressing this analytically is a bit of work. So, it is definitely very clear from this example that an orthogonal or a perpendicular coordinate system has its advantages. It is always nice to have a perpendicular coordinate system in 2-dimensional space to represent any 2-dimensional vector. The same idea can of course be extended to 3 dimensions and then one could also conceive of more than 3 dimensions, 4 dimensions, n dimensions, and then in principle an infinite number of dimensions too. Now, there again when we talk about infinite dimensional situations, we have countably infinite and uncountably infinite, finer points, but for the moment infinite is difficult enough. So, infinite dimensional vectors in fact lead us to the idea of functions. Now, it is a little difficult to understand infinite dimensional vectors all at once. So, to progress towards infinite dimensional vectors, it is easier first to start from finite dimensional vectors of larger and larger dimension. And all that we need to do is to understand that what characterizes the dimension of a vector is really the number of independent coordinates that it has. For example, a 3-dimensional vector has 3 independent coordinates. A 4-dimensional vector would have 4, an n-dimensional vector n, and an accountably infinite dimensional vector would have a countably infinite number of dimensions or a countably infinite number of coordinates. By countable, we mean we can put the coordinates or the dimensions in 1-to-1 correspondence with the set of integers. So, we can talk about the 0th coordinate, we can talk about the 1th coordinate, we can talk about the -1th coordinate, the -2th coordinate, and so on and so forth. What are we talking about here then? If we talk about an infinite dimensional vector, we are in fact talking about sequences. So, we will build up the idea from there. So, here we are. Let us make a note of this. An infinite dimensional vector, or rather an countably infinite dimensional, vector is essentially a sequence. So, for example, we have a sequence x of n, where n belongs to the set of integers over all the integers. Recall that this script z is a representation of the set of integers, and this is called the index variable. So, now we have a different interpretation for sequences. A sequence is like a vector, and each n is a different dimension of that vector. Okay? I think that is important enough for us to write down explicitly. So, a sequence is a vector. Each n is a different dimension of the vector. And once we have this analogy, then extending other ideas of vectors to this context is not difficult at all. For example, adding two vectors, simple, add the sequences point by point. Multiplying a vector by a constant, very simple, multiply each point of that sequence by that constant. What we would like to do now is to extend some of the other ideas of vectors that we have, some of the geometrical ideas to this context of infinite dimensional vectors. And one of the very useful ideas that we have in the context of vectors is the idea of a dot product. How do we take the dot product of two vectors in two dimensional space? So, let us recall. So, suppose for example, we choose a pair of orthogonal coordinates. So, we have u 1 cap and u 2 cap as we did some time ago, orthogonal to one another, perpendicular to one another. And we have two vectors, let us call them E 1, which has the coordinates E 1 1 and E 1 2. So, E 1 is E 1 1 u cap u 1 cap plus E 1 2 u 2 cap, and similarly E 2 as a vector has the coordinates E 2 1 u 1 cap plus E 2 2 u 2 cap. Then the dot product of E 1 and E 2, E 1 dot E 2 as we write it, is essentially E 1 1 E 2 1 plus E 1 2 E 2 2. So, it is the sum of products of corresponding coordinates. Two dimensions easy enough to understand. 3 dimensions easy to extend. In fact, n dimensions equally easy to extend. Suppose we had two n dimensional vectors characterized by coordinates say E 1 1 to E 1 n. So, you have two n dimensional vectors. E 1 characterized by coordinates E 1 1, E 1 2 up to E 1 n, and similarly E 2 characterized by the coordinates E 2 1, E 2 2 up to E 2 n. Then of course, E 1 dot E 2 is easy to express if we generalize this. It is essentially summation k from 1 to n E 1 k times E 2 k. So, dot product generalized to n dimensions. Of course, we assume these are orthogonal coordinates. Now, we can even take this to infinite dimensions. So, we can think of the dot product of two sequences, let us say x 1 and x 2. So, we have here for example, two sequences x 1 n and x 2 n defined over the set of integers n over all the integers. Their so called dot product or inner product, as the formal name is. So, you see instead of dot product now, we would like to use the term inner product to generalize, and we denote the inner product this way. For the moment, let us assume these are real sequences. For the moment, In that case, if we generalize, it is easy to see that the inner product of x 1 and x 2 is simply summation on n running from all the way from minus to plus infinity x 1 n times x 2 n. And of course, it is clear that the dot product or the inner product, as we are going to call it in this generalized situation, is commutative. That means, if I interchange the roles of x 1 and x 2, the result does not change. However, we would like this inner product or dot product notion to give us some of the powers and some of the conveniences that the dot product offers in the context of vectors. One so called convenience or one so called interpretation or meaning that we derive from the dot product is the notion of magnitude. So, in fact, one could think of the notion of magnitude as induced from a dot product if one desires, or in other words, one could calculate the magnitude of a vector by using the notion of a dot product as one path towards the calculation of magnitude. Incidentally, the word magnitude of vectors is used for small dimensional vectors like 2 and 3 dimensional. But when we go to these generalized situations of n dimensional vectors or countably infinite dimensional vectors, we replace the word magnitude by the word norm. So, we say that we would like the squared norm of x to be the dot product of x with x, as is the case with vectors. So, if you recall, A dot A, where A is a vector in 2 or 3 dimensions for that matter, is the magnitude squared of A. The same should hold good here. When we take the dot product of a sequence with itself, it should give us the squared norm of that sequence, where norm is a more general word for the magnitude. In fact, in L2R, the norm is representative of the energy, but at this moment we are not talking about L2R, because we have not yet come to the situation where we are dealing with functions of continuous variables. So, we will postpone that interpretation for a minute, not very far away from now, and once again come back to sequences. Even for sequences, when we take the dot product of a real sequence with itself, we indeed get something that we liken to an energy of the sequence. So, it is not uncommon to refer to the dot product of a real sequence, or for that matter sequence with itself, as the energy in that sequence. Anyway, I kept emphasizing real for a good reason. When we talk about the magnitude of a vector, or for that matter the more generalized word norm, what is it that we expect of a magnitude? We want the magnitude or the norm to be a non-negative number, and in fact strictly positive if that vector is non-zero.